We're collaborating with other colleagues, in particular with Professor Christine Van Vliet in the biological engineering department. And once again, these cells, they're used for therapy. They grow the cells and they try to multiply them so they can implant them on a patient to cure certain conditions. So it's very important for my colleagues to quantify how the cells grow. They need to grow fast enough so they can be available to the patient. They need to grow safely, make sure the cells do not become toxic or somehow infected, in which case obviously they're going to do a lot of damage. So in this particular case, we did not address the second point, not the potential toxicity, we addressed the growth. Simply by counting the nuclei of the cells, we can tell our colleagues how fast their cultures grow or how slow. And of course, why the nuclei? Yes, because the nuclei kind of stand out, right? Everything is transparent, but there's, if I can say so, there's a little bit more nucleus than the rest of the cell. So you can actually capture the nucleus more reliably with the algorithm. Traditionally, one way to do this, exactly because things are transparent, traditionally people modify the cells genetically and they make them fluorescent. This was another Nobel Prize, more recent this one, I don't remember the year, but one of the most celebrated Nobel Prizes actually. But still there's a problem, because if you do this modification to the cells, then you are not really studying the cells in their native state, you are studying them after you have modified them. And that can create some uncertainties, right? You know, did that modify the biological function or might have other repercussions? So yeah, we can do all of this without any fluorescence. It is a sort of just light going through the cell, and a pretty low intensity light too, so we don't actually fry, so to speak. Another collaboration we have with my colleague next door, Professor Nick Fang. Stereolithography is a very nice way to make artificial materials. And what do I mean by artificial materials? Materials that have properties that you do not find in naturally variable materials. For example, hardness or optical properties, optical thickness or sound properties to make materials perhaps soundproof or the opposite, completely transparent to sound. So there is natural materials that have desirable properties, but they reach limits, right? So what colleagues like Nick Fang do, and we're helping them in this case, is to engineer very fine structure, structure that could not be visible to our eyes. But because they design it in a certain way, this geometry can actually provide these desirable properties to the material, even though they would never be found in nature. And the scales come because, as I said, these structures are very, very tiny. But of course, a tiny object is not very useful to a human. We need to pick it up, to touch it, to interact with it. So you really have to fill a relatively large space with these microstructures so that you can make it useful to a human. So that's another very big topic that involves a lot of interaction between material science and imaging. Obviously material science, because you need to actually pattern. These are still natural materials, but we have to pattern them in very, very demanding ways. And also you need imaging so that you actually know what it is that you're patterning, if it makes any sense, you know. If you do it blindly, you may end up with a pattern that is not really what you wanted to do. So we're trying to image them, and that's challenging too, because these are very tiny and not necessarily friendly to light. So we need to overcome a lot of challenges, including again computation, to make them quantifiable. Actually, my own research is fairly narrow, but I think you are gathering that we can collaborate with a lot of people, because some of these collaborations are sort of very scientific, some of them are very applied. We're working, for example, with pharmaceutical companies already through collaborations by MIT. We're working with them to improve their drug manufacturing, their pharmaceutical manufacturing lines. Then, as I mentioned, there's a lot of applications in medicine, especially X-rays. But of course, medicine requires an extra step, which is that it has to go through the various approvals and clinical trials. and so on. We're working, for example, on a project. This one is in Singapore with my MIT Singapore affiliation. We're working on a project on glaucoma, understanding the origins of a very serious cause of blindness. So again, we're collaborating with clinicians, trying to push this technology to practice as soon as we can, of course, provided we get the necessary regulatory approvals. Then there's other things that how can Intel put a synchrotron in their facility? Well, obviously that project is a little bit more early, right? At least before wider adoption. And then there's other sort of even more exotic things that veer more to the scientific side, right? You know, we're trying to study some fundamental processes about cells, for example. Again, these are very far from adoption, regulatory approval and consumption. So we cover the whole spectrum, and it's also kind of fun, right? Because, you know, the very fundamental projects typically, surprisingly actually, how often you are working on something that appears very fundamental and, you know, very curiosity driven and very out of the blue. And suddenly you realize that on the way of doing that esoteric thing, you get an idea that you can use then in another project that is very close to industry and very close to commercialization. So I think that's very healthy to have this kind of interface, and I also encourage my students as much as they can, each student to do both, to be involved in fundamental as well as applied